Okay, hello everyone. This is the second exercise we are putting on YouTube for the Erasmus guys, and not only everyone that wants to check it out in English version. So this is one of the exercises we are dealing with this week, and basically it's in Portuguese, but I will translate for you guys. We have the stress state defined by the stress tensor you see here. Okay, in the format you are used with. So that means we'll have the normal stresses over the diagonal of the stress tensor, so sigma xx, yy, and zz, and we have the shear stresses out of the diagonal in the stress tensor, reminding that we have here is a symmetric matrix. And the problem is to obtain the principal stresses and principal directions. So this tensor is defined on this referential xyz, and the definition of principal stresses and principal directions is to find a new referential. So this is the original where we have the stress tensor. So the purpose is to find a new set of x's that I will call n1, n2, and n3. So random orientation. And in this new referential, that is still a Cartesian frame with all axes orthogonal, and in this new axis we are going to have here sigma 1 principal stress 1, and 2 I will have sigma 2, and 3 sigma 3. So basically we are transforming this stress state. We are not actually transforming, we are expressing this stress state in another referential, and in this another referential we are only going to have 3 principal stresses and no shear at all. And this is possible not adding any force, not adding anything, so it's the same stress state, but instead of using the axis y, x, y, and z, I'm going to use this new referential n1, n2, and n3. So for those familiar with algebra, this is the very same problem you find in a square matrix, the eigenvalues and eigenvectors. And so we can state that the principal stresses are going to be the eigenvalues of the matrix, and the eigenvectors will be the principal directions. Okay, so it's pretty much what you saw in algebra, and because of that you can look to any algebra book and you know that there was this equation where we could solve the determinant of your matrix A minus some lambda, that will be the unknown, times the identity matrix, so the diagonal matrix with ones over the diagonal, and equals to 0. So you solve this determinant and then you can find a polynomial, and this polynomial of third order will have 3 roots. So this is what you see here. Okay, so I'm basically grabbing this tensor, completely general. I'm taking out from the diagonal our unknown sigma over the diagonal, so I'm basically applying this formula, but here I will have the tensor sigma, and here I'll have the unknown sigma. Okay, so some confusion. So sometimes instead of using sigma, we use a lambda, but anyway, you have here this lambda. And so if you solve this determinant, there is many ways you can do it. You can use, for instance, the so-called Sarrus rule, where you basically copy the first two lines and make cross products. So just check for this on Google. And if you apply Sarrus rule to solve this determinant, you will end with this polynomial, with a third order polynomial. And you see here that we define these three quantities, I1, I2 and I3, that we call it the invariants. Okay, the name invariants, it's self-explainable because these values will be always the same no matter which referential you are using, either the principal directions referential, the original, or any other referential. They are always the same, and they will be basically expressions dependent on the components of the stress, because what we did here, we made the rule and we got some train of components, and all the components depending on the square of the unknown sigma will be I1, depending on the linear component will be I2, and the constant will be I3. So I will put everything here, so you can basically pause the video and try to make the determinant by your own. And in the end, if you collect all the stuff, we got these expressions for I1, I2 and I3. And we can now start to solve our exercise. So I will just put here the rubber. And so let's try to see in which referential will give us the three principal stresses. Okay, so we will start calculating. Let's start calculating the three invariants for our problem. Okay, so I recommend you once again that you calculate the values by your own. Okay, so you maybe can pause the exercise now, and let's calculate the invariants and solve the polynomial. Okay, so our first invariant will be basically the diagonal of the matrix, and so you just need to sum the three values for x, y and z. So if you go to our tensor, it will be 6 plus 3 plus 3, 12. Second one will be 44. Third one will be 48. So in the end, the polynomial you want to solve will be this one. And so you can easily solve this one using any calculator, but I usually use this class to remind you about a rule that is the Ruffini rules, that allows you to transform a third order polynomial into a second order one. And to perform Ruffini's rule, you need to know which term, or you need to know basically that the roots of this polynomial are terms that can divide this constant coefficient. And so we have a lot of possibilities, because 48 can be divided by 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and so on. But this exercise gives us a bonus, and I will close up this one. And remember that when we have let me put this smaller. When we have a principal stress, we basically want to have the three principal stresses expressed in a referential where I have no shear stresses. And if you can see here, we already have this pattern over here. So that means that 6 is actually a principal stress because it has no shear associated. So tau, x, z, and x, y are 0. And so because 6 is our sigma x, so I can state by logic that the principal direction will be the x-axis, okay? And so we already know one of the principal stresses. So that means I can apply Ruffini's rule using this term. So just to remind you about Ruffini rule, here is the term that can divide the polynomial. I will put here the coefficients for the cubic, square, linear, and constant terms. So the first one goes down, and now we will multiply 6 times 1 and sum with minus 12. That will give us minus 6. 6 times minus 6 will be minus 36, and then I sum with 44, it will be 8, and then 6 times 8, 48. So we know that is a root because in the end you need to get 0. So you can easily say then that our polynomial will be equivalent to sigma minus 6, the root, and now we have here the quadratic term, the linear term, and the constant term. So it's a second order polynomial, so we know that 6 should be the sum of the two roots and 8 should be the multiplication of the two roots. So you can try to guess, but you can pause, and we know that 6 is the sum of 4 and 2, and multiplied they are 8. So this is the same that stating that we have sigma minus 4 and sigma minus 2. So in this sense, we can state, putting on order, that sigma 1 will be 6, sigma 2 will be 4, and sigma 3 will be 2. Okay, and we are working with megapascal. And now we know this direction, that is our x-axis, but we still don't know n2. Okay, so how to do it? We are going to use the Cauchy formula that we learned in the previous weeks, and in Cauchy formula we know that the resultant stress can be obtaining projecting the stress tensor in some direction. So what I'm trying to do here is the following. So if I have my tensor from our exercise, and now if I take, so let's determine now n2. So if I subtract from the diagonal sigma 2, so sigma 2 is 4 megapascal, minus 2 and minus 2. So basically I'm taking out the contribution of this principal stress that acts on the second principal direction. So what I'm doing here is the following. I'm taking the contribution, so this should be 4. This is our, not 2. Black again. So minus 4 and minus 4. So we know that on the second principal direction we have sigma 2 acting. So if I take this contribution and if I project in the direction, the resultant must be 0. Because basically I'm taking all the stress that is acting on this direction. And so this will give me a very simple system of 3 equations for 3 unknowns. So if I multiply now the matrix by the vector, I will have 2L2, 0M2 and 0N2. So from this one you know that L2 is 0 mandatory. Second equation, 0L2 minus M2 n plus N2 equal to 0. And for the third equation we have 0L2 1 M2 minus N2. And so you see that these two equations will give you the same information. M2 and N2 should be the same. So you can state that any vector in the form of 0, k and k, for any k, so I can put any k, it's a solution. So we can state, to be quite simple, that k, so let k be 1. So our vector will be the vector 0, 1, 1. But any axis must be unitary, so the norm must be 1. So we are going to normalize this vector. Okay, so to normalize this vector we basically divide by the norm, the modulus. So N2 will be 0 square 2 above 2 square 2 above 2. And so we have already the second direction. So to get the third axis, N3, the most correct way is to use a square product. Sorry, a cross product. So we know N1, you know N2. These two vectors will form a plane. So any referential must be formed by 3 mutually orthogonal axes, and the third axis, N3, must be formed by the cross product between N1 and N2. So that's exactly what we're going to make it here. Plus, it's way more simple than performing Cauchy formula again. So performing this cross product should be easy. So let's make it very quickly here. It's also important to make the cross product. So let's imagine for any two calculation you use like -1 instead of 1. So that will be negative, but we will still manage to make a correct referential by performing the cross product over here. So the first term will be 0, the second term will be minus square 2 above 2, and the third one will be positive. So basically what we have here, in the end of this exercise, we had this original referential, and in the end, if you see, our N1 was coincident to X, N2 was a 45 degrees inclined to Y, and N3 is here. So if you project and calculate the cosine directors, that's exactly what we got here. So this is the basics on how to taking principal stresses and directions. Okay.